All right, if you've ever prepped for a tech interview, you have definitely seen this problem. We're talking about spotting those impossible loops, or cycles, in data. And this pops up everywhere, from scheduling tasks to routing network traffic. Today we're going to break down exactly how to find them so you can absolutely master this fundamental concept. Let's get into it.
Okay, picture this. You're building out a project plan. Task C needs task B to be done, and B needs A. Super simple, right? But then, what if somewhere down the line, someone makes task A dependent on task C? And boom, you're stuck in an impossible loop. That loop is a cycle, and spotting them is exactly what we're going to nail down today.
So let's get official for a second. What is a cycle? Well, formally, it's a path in a graph that starts and ends at the very same spot. You can just think of it as a closed loop. It's a fundamental idea, and finding one changes everything about how we can handle a graph. To really wrap our heads around this, let's use a simple analogy. Think of a graph as a city map. Now, the big question is, are the streets one-way or two-way? Because believe it or not, that single difference splits the entire world of cycle detection into two totally separate problems.
So this slide really breaks down those two worlds. On the left, you've got directed graphs. These are your one-way streets. A cycle here is like getting stuck in one of those traffic loops you can't escape. It completely breaks any kind of logical ordering, what we call a topological sort. Then on the right, you've got undirected graphs, where every street is two-way. Here, any closed loop at all is a cycle, and finding one is how we know for sure that a graph isn't just a simple tree.
All right, let's dive into that first one, the one-way street problem. How do we find out if a bunch of dependencies or prerequisites has an impossible loop baked into it? Well, we have two fantastic algorithms for this.
First up, we've got a real classic, depth first search, or DFS, but with a clever twist, a coloring system. It's like you're an explorer in a maze. You mark nodes white if you haven't been there. When you start exploring from a node, you color it gray. That means, hey, I'm currently on this path. Once you've checked all its neighbors, you color it black, all done here. Now, the magic happens in step 3. If you're exploring from a gray node and you stumble upon another gray node, you've found a back edge. You've circled back to a node that's still on your current path. And that, my friends, is a cycle. Guaranteed.
Now, method number 2, Kahn's algorithm, flips the script entirely. It thinks about everything in terms of prerequisites. First, we just count how many arrows point into each node. That's called its in-degree. Any node with an in-degree of 0 has no prerequisites, so we can tackle it right away. We toss all of those into a queue. Then we just start pulling them out. Every time we process a node, we tell all its neighbors, hey, one of your prerequisites is done, and we lower their in-degree. If a neighbor's in-degree hits 0, great, it's ready to go, so into the queue it goes. Now, if we get through every single node this way, there are no cycles. But what if the queue goes empty, and there are still nodes left over? That's our proof. Those leftover nodes are hopelessly trapped in a cycle.
And here's the best part. Both of these methods are incredibly efficient. Their runtime is O of V plus E. In plain English, that just means they're linear. The time it takes grows right alongside the size of the graph. We basically just touch each node in each edge one time. So for huge data sets, these algorithms are perfect.
Okay, time to switch gears. Let's talk about our second world, undirected graphs, the two-way street problem. Here, connections go both ways, and that completely changes our strategy. We can't just look for a back edge anymore, because if you go from A to B, of course you can go from B back to A. That's not a cycle. We need a much smarter check.
So for these two-way streets, we can still use DFS, but we add one clever little trick. As we explore, we just remember the node we just came from. We'll call it the parent. So when we're at a node, looking at its neighbors, if we find one we've already visited, we ask a simple question. Wait, is this the node I literally just came from? If the answer is no, bingo, we found a cycle. It means we found a different way back to a node we've already seen.
But there's another super powerful method called union find. And the analogy for this one, it's awesome. Just imagine that every single node in your graph starts out in its own separate apartment building.
Okay, so how does this apartment building thing actually work? Well, we go through our graph one edge at a time. For an edge that connects, say, node U and node V, we ask, are U and V already in the same building? We use a find operation to check. If they are, we've found a cycle. It means there was already a path connecting them, and this new edge is just redundant. If they're in different buildings, we do a union operation, basically merging the two buildings into one big complex. And we just keep doing that until we either run out of edges or we find that one edge that connects two nodes already in the same building.
Okay, so we've got 4 algorithms on the table. DFS with colors, cons, DFS with a parent check, and union find. In that high-pressure interview hot seat, how on earth do you choose the right one? Let's put them head-to-head.
This table is basically your ultimate cheat sheet. For directed graphs, DFS and cons are both fantastic with that same efficient OOV plus E time. The choice really depends on what else you need. DFS is pure detection, while cons actually gives you a valid task order if one exists. For undirected graphs, you've got DFS with a parent check or union find. Now look at that time complexity for union find, O of E alpha of V. That little alpha symbol is the inverse Ackermann function. You do not need to know the math behind it. Just know this, it grows so slowly that for any graph you'll ever see, it's basically a constant. This makes union find ridiculously fast. So the takeaway? First, know if your graph is directed or undirected. That cuts your choices in half. Then pick the best tool for the job.
Okay, before you run off and start coding, let's talk about a few common traps people fall into. First, and this is a big one, topological sort is only for directed graphs. Don't even think about it for an undirected graph. Second, don't forget the easy stuff. A node pointing to itself, that's a cycle. 2 edges between the same 2 nodes? Yep, that's a cycle too. And a subtle coding gotcha, make sure you account for all your nodes, even the ones that only ever show up as a neighbor.
All right, theory's one thing, but getting your hands dirty is where this stuff really sticks. Let's look at a few classic problems where these exact algorithms are the key to unlocking the solution.
If you want to practice, these 4 problems are absolute gold. They show up in interviews all the time. Course Schedule 1 and 2 are your classic directed cycle problems, perfect for practicing both DFS with colors and cons. Then graph-valid tree and redundant connection are fantastic for the undirected side. You can solve them with a DFS parent check or see just how fast union find really is.
So if you remember one thing today, let it be this. Cycle detection is all about different ways of spotting a loop. DFS looks for that back edge to a path you're still on. Cons looks for nodes that get left behind. And union find pinpoints the exact edge that creates a redundancy. It's that simple. And now you've got the whole toolkit.
So we've totally nailed cycle detection. But, cycles are just one pattern in the massive, fascinating world of graphs. I mean, what about finding the shortest path between 2 cities? Or finding clusters of connected friends in a social network? What other secrets are these structures just waiting to tell us?